Hi, welcome back. Let's talk about scientific notation for a minute. If you can imagine performing math operations with very large or very small numbers by hand, then you can automatically see one of the benefits that using scientific notation has to offer. Likewise, logarithms are used for dealing with very large or very small numbers, and we'll talk about those coming up pretty soon. The opposite of scientific notation is standard notation. If you were asked to write out a very large number, 1 million for example, standard notation is how you would do it. Let's talk about the rule here for a second. A number is written in scientific notation if it has the form a times 10 to the n, where the absolute value of a is a number between 1 and 10. Let's look at this in the context of some examples. In the table here, you see standard notation of some numbers on the left, and the scientific notation of those same numbers on the right. 0.0000000, I've already lost track. 1 is a very, very small number. But if you count over, you can see that when you get to 1, that is, the decimal place is on the right side of 1, you moved over 10 spaces. To get back to standard notation, you'd have to go back to the left 10 spaces, or a negative 10 spaces. Therefore, the standard number in scientific notation is 1 times 10 to the negative 10. Let's take a look at the next one. You have 0.0003, and it's a negative. So if you count over 1, 2, 3, 4 spaces, what you get is negative 3 times 10 to the negative 4th. So these are very small numbers. But the same thing applies for larger numbers as well. The number we have here is 1 million, which we know is a 1 followed by 6 zeros. Since the goal is to get the number between 1 and 10, to write this in scientific notation, you would have to move the decimal place 6 times, which will give you 1 times 10 to the 6th. The reason the 6 is positive here is because, from scientific notation, you would have to multiply 1 by 10 to the 6th to get the number in standard notation, or 1 million. Next one's a quicker example, 3,000. In scientific notation, you would write this as 3 times 10 to the 3rd. This makes sense because if you wanted to write the number in standard notation, and you multiply 3 by 10 to the 3rd, which is 1,000, that'll give you 3,000. We can also look at this in terms of something we just covered, the negative exponent rule, when we were talking about rules for exponents. Observe the number 1 times 10 to the negative 10. The negative exponent rule says that when we have a base raised to a negative exponent, it should be the same thing as 1 over that base to the positive exponent. In this case, we have 1 times 10 to the negative 10th. The 10 to the negative 10 is the same thing as 1 over 10 to the 10. So we should have 1 over 10 billion. In decimal format, that corresponds to the number that you see here. If you count the decimal places back over to convert it to scientific notation, you'll get the number that we started with here. So in the previous slide, we were dealing with a very small number. If you wanted to put it in words, you could say we were dealing with a number that is 10 1/billionths of a whole number. But here, we're actually dealing with 10 billion. So how would we write that in scientific notation? Well, just like we use a negative exponent rule to divide by 10 billion, since this is a positive number, we're multiplying 1 by 10 to the 10 billion, or 1 times 10 to the 10. Let's go over some examples here to kind of help illustrate the point. On the left, we have numbers in scientific notation, and we're going to write them in standard notation on the right. So on the left here, we have 3 times 10 to the 8. The units here are meters per second, which is roughly equal to the speed of light. If you were to write this in standard notation, you're multiplying 3 by 10 to the 8. 10 to the 8th is 100 million. So on the right-hand side, you would count 8 decimal places to the right, and you'd arrive at your number in standard notation. So that's 300 million meters per second. Below that, we have a very small number. In addition to it being small, it's also a negative number. So we keep the sign on the negative number. And since the exponent is negative, we count decimal places to the left. In this case, we count over 7 decimal places. 1 decimal place for the 3, and then 6 zeros. So in standard notation, we would have negative 0.0000003. Below that, we have a negative exponent, but it's a positive number. So we keep the positive sign in front of the number. And starting at the 4, we move the decimal place over by 1, and then we do that 12 more times with zeros. And the number you get on the right is that number in standard notation. Now we have a negative number, but a positive exponent. Well, the number is negative, so we keep the negative in front of the number. But since the exponent's positive, we count decimal places to the right. So starting at 2.5, we move it one decimal place over, and then we add 4 more. And what that gives us is negative 250,000. Below is pretty much the same example, but instead of the number being negative, it's positive with a positive exponent. So the difference between this and what we got above is that 250,000 is positive instead of negative. Let's do a couple more. We have 2 times 10 to the negative 5. It's a positive number, but the exponent is negative 5, so it's really small. So we count over by 5 decimal places, filling in zeros for what we don't have, which gives us the number you see on the right here, 0.00002. And then finally we have 1.9 times 10 to the 2. It's a positive number and a positive exponent. So starting with 1.9, we count 2 decimal places to the right, filling in zeros for the empty spaces, which gives us 190. Let's state what we've been talking about in another way. So when you're dealing with scientific notation, if you have positive exponents and you're converting from scientific to standard notation, you're really multiplying by factors of 10. If you're dealing with negative exponents, and this is an agreement with the negative exponent rule, you're dividing by factors of 10. We're reiterating the rule here because, according to scientific notation format, the absolute value of a must be between 1 and 10. It can include 1, but it can't actually equal 10. So it can be 9.9999, but it can't be 10. And here it is. So on a quiz or an exam, they may ask you to convert these numbers that are in pseudo-scientific notation to scientific notation. In this case, you have 10 times 10 to the 9, but the decimal place should be one more to the left here. So if you were to write this in scientific notation, it would become 1 times 10 to the 10. A similar case occurs for 10 times 10 to the negative 9. If the decimal place were where it should be, you'd only have to take the decimal place 8 places to the left to arrive at the correct number instead of 9. So in this case, it would be 1 times 10 to the negative 8th. Now, a good way to do this and to check your work is to take the numbers out and either multiply or divide, convert them into those types of problems. We've done this for the top example, 10 times 10 to the 9th. And you can see here that we're starting out with 9 zeros, but because it's a 10 instead of a 1, we're adding another 0. In this case, you have 10 zeros, so the correct scientific notation form would be 1 times 10 to the 10. Same thing for 10 times 10 to the negative 9th. If you take the number 10, divide it by 1 followed by 9 zeros, one of those 10s cancels out, and what you end up with instead of 9 zeros are 8 zeros. So you can say that in scientific notation, this could be correctly written as 1.0 times 10 to the negative 8th. Now, sometimes the exponential numbers are very large, but if you need to just remember how to adjust it, you can use smaller numbers for an example. So you could say 10 times 10 to the 4th. So if you worked out 10 times 10 to the 4th the way we've done here, what you'd actually get is 1 times 10 to the 5th. So using a smaller example like that can be a quick reminder to let you know which direction to move the decimal. Okay, let's go ahead and take a break here. When we come back, we're going to work some more problems converting numbers from standard notation to scientific notation and pseudo-scientific notation to true scientific notation.